get started. We are very happy to have Tim Cohen join us today from CERN. Tim received his PhD in physics from the University of Michigan in 2011. He was then a research associate at SLAC before moving to Princeton in the IS, and eventually the University of Oregon, where he was assistant professor. Tim is a phenomenologist with broad interest in particle physics and cosmology beyond the standard model. He's won several awards for his work, and we're very lucky to have him with us today. So he can tell us about whether our universe is eternally inflating, which is good to know, and connections between effective field theories and the theory of large deviations, which I'm particularly excited about. So thank you, Tim, for telling me.
Hello, everyone. It's my absolute pleasure to be here to tell you about some series of papers that I've been working on over the last 5 years, which has ultimately led us to ask some of the most dramatic questions I've had the opportunity to ask in my career, namely, what is the fate of the universe? Okay. So, but since I'm going to be here for a few days, before I get into that, I just want to introduce myself very briefly. So as Reed said, I see myself as someone who thinks about beyond the standard model, be that the standard model of particle physics, the standard model of cosmology, really just trying to push into new territory anywhere I can find it. As a theorist, to me, what that really means is it's this idea of connecting any kind of speculative theory ideas to experiment. So really trying to extend what we know, but always with this desire to be grounded in what's really happening in nature, okay? And so the thing that I love the most about being someone who thinks about BSM is that we really have no boundaries. And as you'll see today, thinking about some ideas in using techniques from effective field theory, which have been traditionally developed in the context of standard model physics, even sometimes beyond the standard model physics, has led to some really exciting new technology that we can apply to thinking about the early universe. Okay, and so here's just some random things I'm thinking about recently. If I get a chance to tell you one-on-one about some really fun ideas we have for BSM that could be showing up in Nanograv. And today we'll talk a lot about this so-called soft de Sitter effective theory. I also think about data analysis, machine learning, so I'm sure we have tons of synergy, and I'm really excited to spend time telling you about what I'm excited about and hearing about what you're up to. Okay, so let's get into the topic of this talk, which is we want to ask deep questions. So what's the deeper question than what is the fate of the universe? Okay. Now, that sounds extremely dramatic. Let me tell you what I really mean, which is I want to understand whether or not the universe we live in is in this kind of strange phase known as eternal inflation. So if you're not familiar with eternal inflation, here's the basic picture. We have this idea that the universe before the Big Bang underwent this period of accelerated expansion that we call inflation, and that the fluctuations of the inflaton were imprinted as what we now see as density perturbations in dark matter today. And the standard picture in the simplest models is that we have a single field undergoing a slow roll down of potential. Okay, so that's what I'm illustrating here. And at some point, inflation ends, okay, something dramatic happens, and that leads to what we call the Big Bang. But because the inflationary period is in de Sitter spacetime, de Sitter spacetime has a horizon, and that horizon leads to an effective temperature. So that temperature feeds quantum fluctuations of the inflaton field. So it's not just the classical evolution, this so-called drift, that's important, but it's also these quantum fluctuations or thermal fluctuations, depending on the picture you're using, which cause the inflaton to bounce up and down this potential. So in the standard picture, the quantum fluctuations are small, and the inflaton just rolls down until it hits the end. But if this quantum noise becomes a dominant effect, which can happen in some models, say where the potential is extremely flat, then all of a sudden the random walk caused by this quantum noise can push us this way, away from the end of inflation. And in principle, that means that there will be patches of the universe that are continuing to inflate always. And so that's very different from this picture where we start inflation, the field rolls, it ends, it starts the universe. Instead, in an eternally inflating universe, we have to confront ideas like the multiverse. And in particular, the thing about eternal inflation is that it basically obfuscates our ability to make predictions. So it leads to so-called measure problems. It's not well understood. It's something people have been puzzling about since inflation was invented. And so I think it's critical that we know, is this just an intellectual exercise to think about eternal inflation, or is this something we actually have to confront in our universe? So that's the question I want to ask today. Is the universe that we live in an eternally inflating regime or not? And as you'll see, answering this question is actually quite non-trivial, even in the sort of simplest models of inflation, including interactions. Okay. So here's kind of the main result. So I just want to motivate you to pay attention to a number of digressions we're going to make along the way. So this is how relevant this question is. Here I'm showing, we'll come back to this perturbative validity later, but here I'm showing the parameter space in this so-called effective theory of inflation that I'll describe a little bit later, where there's two parameters that are governing the interactions that would lead to primordial non-Gaussianity. And so we can plot the region that's consistent with the Planck data. So this is 1, 2, and 3 sigma contours. And you can see actually that currently there's some small order of 1 sigma favor for there being some amount of primordial non-Gaussianity. Okay? But what I'm plotting here is the result of our work, which is the first time we were ever able to compute the region where we expect there to be eternal inflation in this simple model that includes primordial non-Gaussianity. And what we found is that even here, which is the point where you turn off all the interactions, that's where this alpha bar parameter that I'll define later is 0, and the speed of sound is 1. Right next to that, we found that the universe would appear to be eternally inflating. And that just sounds crazy, because this is a very small perturbation and having these dramatic consequences on the fate of the universe. And so, in fact, as I'll describe today, that led us into a deep dive to understand whether or not these calculations were valid, and led us to this connection with the so-called large deviation principle, which actually tells us that we, for very interesting reasons, we actually do not have control of this question, and is going to lead us, I'm optimistic, it's going to lead us to new ways of thinking about this problem. By the way, I should also say, I'm delighted to take questions throughout the talk, and then I guess there's going to be a period with refreshments afterwards where we can continue chatting if we run out of time. Okay, so how did we get there? How did we draw this blue region? Well, the tool that we're going to use is the tool known as effective field theory. So I'm going to spend the next 15, 20 minutes just giving you a picture for what effective field theory is, because I know this is a very broad audience, and how it can be applied to these questions of early universe dynamics. And I should say, you know, a number of years ago, I was asked to lecture at the Tazi Summer School. Actually, David was there. And what came out of that was this way too long article describing a lot of these ideas. So if you're interested, I'll just advertise this. I'm quite proud of it. And so you can take a look, and I'm, of course, happy to chat this week or off online sometime. So the thing that gets me excited about effective field theory is that it takes this idea of reductionism and it formalizes it and makes it useful to do new calculations. So underlying so much of, oh, there's something, I don't know if someone asked a question in the chat.
Yeah, dude. I can read it out. Okay. I was trying to watch it. Question from Sri: how appreciable is the effect of quantum noise?
That's a great question. You'll see, we'll come back to that as we develop the tools we have here. But in the region that I showed in that plot, that blue region, it's not working, here we go. In this blue region, this region has the quantum noise dominating, okay? So in this region, it's a dramatic effect, okay? And again, I'm gonna show you how we quantify this, how we can actually make this, make all of this extremely concrete in terms of formalism and equations as we go through the talk. Thanks for the question. Okay, great. Reductionism. So this is what we do often in fundamental physics, is it turns out that when we zoom in, we learn something new. And so, you know, the history of understanding what the universe is has largely followed this trend. Of course, what's phenomenal about fundamental physics is that we can also use information from astrophysics and cosmology to learn about the smallest possible scales. Nonetheless, the idea is always that we're zooming in, right? And we're kind of here. We want to know what is living beyond the standard model. And the key phrase here is that there's a large separation of scales. And so, I like to pose this question: why didn't Newton and Maxwell need to know quantum field theory in order to make fundamental discoveries about the way the world works? And the answer is that we were lucky enough to live in a universe which manifests many of these examples of a large separation of scales between the size of the atom, the size of the nucleus, the size of the proton, and the size of the quarks, which, as far as we know, is 0. And so the point here is that in a general sense, another of the effective field theory slogans is this idea that heavy physics decouples. Heavy meaning short distance. So when I zoom in, I can learn more, but when I zoom out through the remarkable properties of effective field theory, it turns out that an effective description emerges. I don't have to know that the nucleus is complicated. I can treat it as a point-like object, as an effective description, and I can make a lot of progress. And so the real reason that all of that works is due to this idea of decoupling, that heavy physics decouples. Okay? So what does it mean when I say an effective field theory? What does it mean to build an EFT? I need to know what are the degrees of freedom? What are the modes that propagate? Okay, what's determining the dynamical information? Typically, I need to know something about symmetries. So what are the symmetries that emerge at long distances? And because those are going to constrain the allowed interactions I can write and so on. And then perhaps the most remarkable thing about effective field theory is its marriage of these ideas with dimensional analysis. So effective field theory comes with a notion of dimensional analysis that tells us how to organize our predictions in some way that looks a lot like a Taylor expansion, okay? So EFT always is synonymous with expanding, okay? Again, it's this idea of zooming in, zooming out. So we're always expanding away some information. We're coarse graining in order to come up with some simpler effective description that we can actually work with and make progress, okay? So another of my favorite things in EFT is to emphasize this, we tell freshmen, oh, physics is just dimensional analysis and Taylor expansions. And what EFT does is it makes that true. It's actually the case that when you encounter these situations where there's a large separation of physical scales, you can use ratios of those physical scales to determine a small parameter, and then you can Taylor expand, albeit in a fancy way, in terms of that small parameter, and that's really what effective field theory is all about. That's where the dimensional analysis comes from, is if you can identify a large ratio of scales and you can put it to work, then it all of a sudden opens up the ability to do new calculations, like I'll show you in this talk. Okay, so here in the example today, that ratio of scales is going to be the co-moving momentum of these modes that are produced during inflation, okay, K over A, compared to the Hubble scale during inflation, okay, which is basically, setting the size of the horizon of the de Sitter space, setting the fundamental scale of the expanding universe, okay? So again, I want to emphasize the observables I'll tell you about are expanded in this ratio K over AH. And then, because we're doing an expansion, what effective field theory does is it also predicts the size of the truncation error. You can always make a simple approximation of what you're neglecting because it's higher order in these parameters. So not only does EFT facilitate doing new calculations, but it tells you what the theoretical error is on those calculations, okay? And we all know that science is in the error bars. And so again, effective field theory makes that extremely concrete in telling you how big is your theoretical uncertainty when you do these calculations, okay? Even more remarkably, that's just a property of Taylor expansion. So maybe that's not so surprising, but even more remarkably is that EFT knows when it's valid. It predicts its own region of failure. And that's going to be an important theme today, okay, is that we're going to, because we got this surprising result, okay, it's going to lead us to investigate, is it valid? And we can use the EFT itself to diagnose whether or not the calculation we're doing is robust. okay? So often, if you look at EFT literature, you'll see diagrams like this one. So the idea is we have some fundamental description. I'll often call that the ultraviolet short distance description, okay? We do a so-called matching step, which is we basically take that fundamental description and we match it onto an effective description, okay? So we have these two different theoretical descriptions. Matching is just putting them together and making sure that the predictions of the fundamental theory are being reproduced by the effective theory, at least order by order in this expansion parameter. But when we do this matching, we're doing this at the fundamental physics scale, at short distances. But EFTs are supposed to tell us about long distances. And so in order to actually use the EFT to make predictions, we have to coarse grain. Okay, the technical term is we use the renormalization group to do this, but it's a completely well-defined procedure. And that coarse graining brings us down to the scale where we make predictions for experiments. Okay, so this is the basic strategy. If I can find a separation of scales, I can use that to organize my predictions as a Taylor expansion. Then the job is simply to do this matching and then to use the renormalization group to do this coarse graining so I can make predictions. Okay, and that's the strategy we're going to follow. So before I leave this primer, I just want to mention a little bit more what I mean about coarse graining and then tell you a little bit more about this idea of validity. So we're all familiar with the idea of coarse graining. Okay, so let's say my UV theory is the bunny here, okay? And then I start coarse graining the bunny. So you can see already at this first step, I've thrown away a ton of information, right? It doesn't have fur anymore, it doesn't have any color. And then I use less and less of these spheres, okay, until ultimately I get down to my EFT, my infrared long distance description, which is just a spherical cow model of the bunny, okay? So in principle here, I have a very simple model. And if I was very far away, let's say I was only interested in the motion of the bunny, I don't care that it has ears or legs or fur. I just care about, say, its center of mass, okay? So there are questions I could ask of the bunny where this description is perfectly useful and makes my life significantly easier, okay? And what I really want to emphasize here is that EFT, one of the powerful things about EFT is you'll often hear people say it's universal, okay? But what that really means is when you organize the predictions this way, following this philosophy, then what you end up with are a finite number of parameters which are describing the long distance physics. Okay, so here, basically this is about as simple as it could get, right? There's very few parameters describing this very complicated detailed UV model, okay? And for those of you who are familiar with Feynman diagrams, this process is known as integrating out a heavy particle. The integration is a reference to the path integral. Okay, so what are we doing here? We're scattering the purple particles, which are very light, and they have this intermediate state, which is this red particle, which is heavy. And if you go far away, you can imagine, you can interpret this diagram in position space as this being two interactions separated by some distance in space-time. And in fact, that's completely the correct way to think about what's going on here. We have local point-like interactions that are mediated by some heavy particle. But if we zoom out, that heavy particle is very heavy. It doesn't last very long. We can't resolve the fact that it's there. And so what we end up with is a point-like interaction between the light particles. And you can, again, follow the same strategy. You can have more complicated diagrams with the heavy stuff inside. And it's going to give you higher and higher point interactions. Okay? So this is pictorially, in terms of Feynman diagrams and particle physics, exactly what effective field theory does for us. Okay. The other thing about coarse graining is this idea of the renormalization group, which I already mentioned. Perhaps the most incredible application of the renormalization group is the application of quantum chromodynamics. This is a case where we're computing the evolution of the coupling constant that appears in quantum chromodynamics. Here on the x-axis is energy scale, and this is the value of this coupling constant. Okay, so this is basically the strength of the interaction between quarks and gluons. And what you see is that it evolves as you change energy scale. Okay, there's data here, and it's consistent with this theoretical prediction. This is a coarse graining procedure. And in fact, at leading order, it's just a simple differential equation. Okay, so you learn to derive this in your quantum field theory course. This we can integrate almost in real time, okay? And what we find is we have a logarithm here in the denominator. And it's a very good approximation that gives us this curve, okay? So what happened when we did this coarse graining, when we computed this evolution equation and solved it? Well, what we did is we summed a tower of logarithms, okay? You could Taylor expand this out. But instead, by solving this differential equation, we've taken an infinite set of those logarithms and we've stuffed them into the denominator here, okay? You think of it like a geometric series. And so one of the themes of coarse graining is that this procedure resums logarithms. And we're gonna see that that's gonna have a profound connection in the cosmological theory in a moment, okay? So I'm gonna use this coarse graining renormalization group. I'll use these terms interchangeably. And let me just quickly say, right, there's another example of applying these ideas to quantum chromodynamics, which is the proton. So when we look at the proton, it's hard to see this, but that says low momentum. So we look at the proton from very far away, it just looks like a ball with charge. But we know when we zoom in that actually it's made of quarks and gluons. Okay, so here we show the 3 valence quarks, and then there's the C quarks and gluons. And this transition can be understood using all of these same ideas, okay? There's a sense of renormalization group evolution, and there's a notion of coarse graining here, okay? Finally, I want to say something about EFT validity. So there are 2 ways EFT can fail. One is very familiar. I already said, it's basically this idea that when we do this coarse graining, we're doing a low energy expansion, it's a Taylor expansion, and so we're truncating, and maybe that truncation is not a good approximation, okay? So maybe we're asking a question about fine details where the EFT is just not valid. That's completely fine. We're asking the wrong question, and so the EFT fails. No surprise, but nonetheless, the EFT knows that it's failing because we know that this expansion parameter is not small anymore, so our expansion's no good. The other way EFT can fail is due to the fact that we're solving the path integral. And when we solve the path integral, we're always doing some kind of expansion around a classical trajectory. And so typically, this is not something you're even necessarily told you're doing, because you take 0 as the background. And for most of the developments of quantum field theory, that's the situation we're in. But of course, here, when we think about astrophysics, we're often in finite density environments, we have finite temperature. Okay, so that is not always the right approximation to make. And there are even more subtle cases, which is going to happen in this talk, where it turns out that we're expanding the path integral around the wrong semi-classical point. Okay, this is very hard to diagnose, and there are only a few known examples of how to put this to work. I'd be happy to tell you about it over coffee later. And we're going to show, what I'm gonna try to argue for you is that this question about the phase transition to eternal inflation is sensitive to some new saddle point of the path integral waiting to be discovered, okay? And so basically, going forward, we're gonna move to inflation. I'm gonna follow all of the rules of EFT. This is the easy part to follow, okay? And I'm gonna end up at that surprising conclusion I showed you in the beginning. And then I'm gonna make an argument that what happened was that there's some new saddle point appearing, and basically whether or not which saddle point you should be expanding around is directly tied to the question you're asking of the EFT, okay? So we're gonna see all of that play out in the course of the talk. Okay, so let me just recap quickly, because I know I told you a lot. What you need to remember to follow the rest is that we get a simpler description of physics in the infrared at long distance. There are typically a few universal parameters, and we coarse grain away short distance dependence. That coarse graining is equivalent to running the renormalization group, some differential equation that we can solve. You'll see a differential equation appear soon that has to do with cosmology. And the key phrase there is that we're resumming towers of logarithms, okay? Basically, polynomial things get summed when we do this matching step at the high scale, and any logarithmic correction that appears is absorbed by doing this renormalization group flow, or this coarse graining. And EFTs have a region of validity due to their perturbative expansion, but also expanding around the right background. Okay? Please.
If I was spinning it around the correct background, I mean, would an example of this be something like chiral perturbation theory, or something where you're thinking QCD, where it's in sort of a symmetry broken phase in the low energy theory, or is it something very different?
No, it's different from that. So the example that I know of where this is calculable is this so-called large charge expansion. So if you're asking about operators that are carrying a large charge, then the perturbative expansion can fail, and actually you can solve for a different semi-classical saddle. And then you can compute, all your favorite things in almost dimensions and so on. So we're going to find a very close analogy with the large charge expansion in what we're going to do.
Can I ask a quick question?
Yes, please.
So if you run the high order correlation, aren't you essentially getting the full field theory back again?
Exactly, yeah. So
So I don't really see that logarithms necessarily the correct way the expansion goes with the big number.
well, so I'll show you how this applies in inflation. But basically,
No, I'm asking the general philosophy of line on this.
so basically the point is that the matching is going to absorb anything that's local. Okay, so basically all of when you do this matching between a theory, say with a heavy particle and the theory without, you can absorb all of the local dependence on the heavy particle into the coefficients of operators involving the light particle. But then,
so the non-local, you would consider a gradient expansion of high order being non-local?
no, that would also be local. So anything that's polynomial and say fields and derivatives of fields would all be local. And you can absorb all of the power law dependence of the heavy field into that expansion. But then you also get these logarithms that can appear, which cannot be absorbed into just the simple polynomial expansion of those coefficients in a systematic way that keeps them small, right? So I was glossing over some details here, but the point is that when you have a large ratio of scales, what's going to appear inside these logarithms is that ratio of scales. And the logarithm can become large, and it can overwhelm the small coefficient in front. And so what the renormalization group lets you do is it lets you resum those logarithms and get something that's convergent. So all the polynomial dependence is sort of convergent by definition because it's just a Taylor expansion. But these logarithms, which are actually sensitive to all possible scales, they don't have to stay small. But when you run the renormalization group, you're basically resumming them into a quantity that's always going to stay perturbative.
Yeah, could I just summarize it? So you might end up having an exponent of the log, which will then get you back into power counting.
Yes.
So that's feasible, it does happen.
That's feasible, and that's kind of what's going to happen here in a certain sense. Indeed. So the key is to be asking basically only questions, and this kind of gets to Mike's question, right? The place where we know that this expansion breaks down, where we know we're not expanding around the correct background, is a place where we basically are looking at something with an exponentially high number of legs. Okay, so an operator that's got many, many legs, and exactly as you're anticipating, what happens is then e to the log makes something that was small become large again. Great, thank you. Any other questions about this before we move into cosmology? Okay. So for the rest of the talk, I want to tell you about this so-called soft de Sitter effective theory that I discovered now 3 or 4 years ago with Dan Green, and the application to this question of eternal inflation and the validity of the EFT. Soft refers to the fact that we're going to be describing low energy modes of, say, scalar fields in de Sitter space or of the inflaton itself. Okay, so mostly what I'll focus on in the talk, once I get through some generalities, is applying this to the case of the inflaton. Okay, and then towards the end, we'll connect what happens to this so-called theory of large deviations. Okay, so I should say this is most of what I'll show you is work with Dan Green, who I know is familiar here at CITA, and his former student Akhil Premkumar is now a postdoc in Chicago. Okay, so also well known to many of you is this idea of stochastic inflation. So let me dress this picture that I had early on in the talk with a differential equation. So the idea is if you have some massless field in a de Sitter space, it could be the inflaton itself, or the scalar fluctuations of the inflaton, then it undergoes this competition between drift and noise. And that random walk, you can think of it as a random walk, okay, that this thing is evolving in time and randomly fluctuating subject to this driving potential. And we know how to characterize random walks. We just can use a Fokker-Planck equation. And in fact, Starobinsky's insight, basically right around the beginning of when inflation was invented, was he came up with very much a coarse-graining kind of description for understanding this, and was able to derive this differential equation, which tells us about the time evolution of the probability distribution of this field that's fluctuating. And it has two contributions. This one is the so-called quantum noise, and this one is the drift. Notice that it depends on the potential, okay? So this is driven by the expanding space-time. It's proportional to the Hubble scale, and this depends on the details of the model through the potential. But it's also clear that this must be a leading order picture, because the assumption is that the noise is Gaussian, the potential is classical, it's just the classical potential. But if we have interactions, then we know those interactions lead to some kind of non-Gaussianity, and so there must be some non-Gaussian contribution to the noise. And we know that the potential gets quantum corrections, and so there must be some way to encode quantum corrections in a systematic way. Okay, so that's a question that many of us, there's also recent work from these authors, but that's a question that we can address in this context of the so-called soft de Sitter effective theory. So what does it even mean to go beyond leading order in a Fokker-Planck equation? Well, to understand that, we need to take a step back and ask, where does the Fokker-Planck equation come from? So it turns out that there's a very simple way to see this, due to Chapman and Kolmorogov, which is you just assume that the fluctuations have no memory. Okay, what does that mean? That means that the next time step is completely governed by the state of the system at the current time step. Okay? And then you can just write a simple differential equation for the evolution of the probability, and it's as dumb as this. You take all possible ways that my field can go to the point phi, and you subtract from that all the ways that it left phi to go to other points. Okay? So that's the entire content of this equation. This W is just encoding that transition rate, okay? And that's it, okay? It's really that simple. But of course, this is maybe not useful in a general context, okay? This W thing is non-perturbative. I don't know, you could solve this numerically perhaps, but what do we do when we see very general equations like this? Again, we Taylor expand. So let's Taylor expand this W. Let's assume that it's local in the sense that it's dominated by nearby jumps. So if my field is here, then the most likely place for it to go is close by. Okay, so that's the sense of locality. And you can just expand this in moments. Okay, the details of these formulas are not so important. What is important is that now you can recast that very general equation as something that looks like this. And if you organize it as a polynomial expansion and a Taylor and an expansion in derivatives, what you find is you get the Fokker-Planck equation at leading order. Okay, so this stochastic inflation is indeed leading order in something. Okay, and the generic structure looks like this. Okay, so there's this drift term due to the potential, but then there's in principle a tower of these derivative terms, and that's what encodes this idea of non-Gaussian noise or higher order noise. Okay, so we set ourselves out to understand, are these higher order terms calculable? Can I take a theory from first principles and can I compute corrections to this Fokker-Planck equation, if nothing else to make sure that they stay small? So the tool we want to use to do that is what we call the soft de Sitter effective theory. Okay, so going back to everything I was saying about effective theory, you're going to see all of those different themes now appear in this context. So we want to, here we have a ratio, oh, there's a question.
To be any quantum noise due to photon noise?
Oh, well, yeah, so this is an extremely simple, in this context, this is a very simple universe where I just have some vacuum energy domination, so I have exponential expansion, and I have a massless field, okay? But absolutely, there were to be all kinds of thermal effects that you'd want to take into account if you were trying to do something much more realistic, indeed. Okay, so here we have, I need to find a ratio of physical scales. So here there is definitely a natural scale for an inflating space-time, for a de Sitter space, which is the Hubble scale. Okay, so that sets some kind of horizon. And what we want to do is we want to apply the tools of effective field theory to integrate out the modes that are short distance compared to the horizon, while retaining the modes that are long. And most of you are probably familiar with this idea that modes freeze out when they cross the horizon. And so what we're really looking for is a way to characterize the properties of the modes that froze out following the rules of effective field theory. Okay, that's essentially what the soft de Sitter effective theory does for us. And there's of course a long history to this, and a lot of interesting work that has come out of CITA over the years as well. But this here we're going to follow the playbook that I outlined in that primer part of the talk, and see where it takes us. So we need to know what are the propagating degrees of freedom, and the natural modes to study are the so-called growing and decaying mode that you find if you just solve the Klein-Gordon equation in de Sitter space. Okay. The trick is to figure out the right low energy parameterization of the fields. Okay, if you like, that's the one serious bit of insight you need to have. Otherwise, we're just going to turn a crank. And so it turns out that the soft modes should be written like this: the modes that live in the effective field theory. Basically, we just factor out an appropriate factor of the scale factor A times the Hubble constant for the growing mode and AH for the decaying mode. And this alpha and the beta are the exponents that appear when you solve the Klein-Gordon equation. So for those of you who are familiar with this, you probably have seen those many times. For the rest of you, they basically depend on the mass of the particle. In particular, if I set the mass to 0, then alpha goes to 0, and the growing mode, time dependence is 0 at leading order, okay? But when we do this seemingly innocuous thing of just pulling out a little bit of time dependence, the miracle that occurs is that in the EFT expansion, the time dependence factorizes. So what makes these calculations so hard is that when you start doing, well, even the tree level calculations are hard, and there are people who are working heroically on new techniques to compute correlation functions just at tree level in inflation or de Sitter space. Here, we're more interested in the effect of quantum correction, so we need to do loops. And when you compute a loop, basically what ends up happening is when you solve the Klein-Gordon equation for these modes, what you find is you get Hankel functions, okay? And the Hankel functions are functions of the momentum of the mode, okay, the spatial momentum, and time. And they're special functions. They mix those together. And so now you need to integrate over time. You need to integrate over momentum when you construct a loop. And it's a product of Hankel functions integrated over time and momentum. And it's just hard. It's technically difficult to do these integrals. What the EFT does, and what EFT, when appropriately constructed, always does, is it makes seemingly intractable integrals that were there in the full theory all of a sudden doable. And the key thing that happens is this time dependence factorizes. So by doing this expansion, a minor miracle occurs, which is instead of getting one very complicated integral over special functions, what we get is a very elementary integral over time multiplied by a slightly less complicated integral over momentum. But in particular, conceptually what this buys us is it lets us understand what the low momentum region is and what the high momentum region is. Because what we're interested in is understanding IR versus UV, right? What's a short distance effect? What's a long distance effect? When you have this Hankel function and time and momenta are both convolved together, basically depending, do you take the time limit first? Do you take the momentum limit first? It gets very confusing to understand what you even mean by short distance and long distance. Whereas in the soft de Sitter EFT, it's completely unambiguous, okay? So that's the kind of magic thing that happens. All right, so we've got these degrees of freedom, the growing mode, the decaying mode. We're going to do an expansion as promised in K over AH. Here are the symmetries, okay? We have space-time symmetry. We have a so-called reparametrization symmetry. It's not important. The EFT people know what that means. and we have a shift symmetry if we're going to talk about the inflaton. So there's no potential in this very simple version of inflation. It's just a flat potential. And finally, a wrinkle, it took us a while to realize this, is that we also need to include so-called initial conditions in order to do dot all the I's, cross all the T's. It doesn't matter. And again, I just want to say, for those of you who know it, there's very close analogies with heavy quark effective theory here up to this notion of initial conditions. All right, so we have a de Sitter spacetime. We have a massless scalar field, and we want to understand these fluctuations due to quantum effects. So where is it going to come from? Well, it turns out that the dimensional analysis, which is so key to being able to do EFT systematically, tells us that this phi plus object to the n scales like k over AH. Remember, that's our dimensional analysis factor. That's our power counting parameter. So that's a small number to the alpha, okay? So alpha goes to 0 when the mass goes to 0. We get that from solving the Klein-Gordon equation. That tells us that we have no extra cost, according to dimensional analysis, for having more and more factors of this growing mode phi plus when it's a massless field. That means that phi to the 4th can mix with phi to the 6th. There's no difference in dimension. There's nothing separating those in the EFT. And in fact, we can find that explicitly. We can take, say, some diagram with 6 of the phi's, we pull 2 of the legs together into a loop, and we get something with 4 of the phi's, and they talk to each other, okay? They have the same dimension. So in a little bit more detail, what does that look like? Well, we can take, say, an operator with n legs, contract 2 of them, and that gives us an integral as promised, okay? When we do this integral, what we get is a logarithm that depends on AH, okay? And this is where the renormalization group comes in, is the renormalization group lets us sum these logarithms exactly in the same way we could do it in quantum chromodynamics. What does that look like? Well, here's some fancier version of the formula, but what's really just important about this, we have some time derivative. Oh, and sorry, that's a key thing I forgot to say here. Notice, okay, the logarithm I'm summing depends on the scale factor. The scale factor gives me time dependence. So by resumming these logarithms, by coming up with some differential equation that's going to, whose solution is going to give me the summation of these logarithms, I'm basically computing the time dependence, okay? So that gives me formulas like this. The time derivative of this object, okay, that I'm interested in, gets contributions here. This is, again, some fancier, I should have written the potential here with these coefficients, but, you know, basically you could think there's just one of these if I have, say, an interaction like 4 fields, phi to the 4th, okay, which is a quintessential model people study. And then I get this term from contracting the 2 legs, okay, which is, here I've suppressed Hubble, but it's just proportional to some loop factor times Hubble. And this formula is just some differential equation, okay? It's some renormalization group formula, or coarse graining formula. But then, if I just do a simple integral transform from this phi to the n picture to some probability picture, what I get is the Fokker-Planck equation plus corrections, okay? So what have I done here? I boiled down the question of what is this Fokker-Planck equation and its extension to a question of computing renormalization group evolution in an effective field theory. And
Can I just ask a
yeah.
question? So at one point, talk to Dan on this. At one point, you made the assumption that H equals constant, so you could do angles and all of that.
Yes.
And yet, there is an effective H as a function of field values at the long wavelength limit. And so that has to appear in this. Does it appear in this? That you have, that H is basically like a potential effect, it's like an action, Hamilton-Jacobi action.
So, yeah, maybe, I'm not exactly sure where, if and where it appears off the top of my head. We should chat about that later. The one thing that this definitely gives you is it gives you, so for example, it tells you when you apply this, say, to massless phi to the 4 theory, that you get that the field itself evolves to some non-trivial equilibrium point, right? So there's a sense in which solving this tells you that the field value, right, the background is different from the one where you started. Still all within the perturbative regime, but it definitely encodes that kind of evolution. We need to chat more.
Yeah.
I'm not sure if it's exactly the same thing you're referring to. Maybe not, but.
I mean, it's a really important issue from the sorts of things that we try and do around here, so that's what I thought.
Yeah, I just in the interest of time. Ooh,
No.
very badly over time. Okay, so great. Okay, so let me speed up a bit. We want to basically we want to apply this to some simple setting. Okay, so here's another use of EFT in this literature and certainly in this talk, which is we can also apply these same ideas to inflation itself. And so this is the so-called EFT of inflation. Is in this first pointed out in this paper here. You basically can understand the inflaton as an effective degree of freedom. What this does is it gives a universal long-distance description of a huge class of slow roll inflation models. Okay, so that's really all that's important. And the idea is that the EFT of inflation has its own region of validity. The soft de Sitter effective theory kicks in a little lower. Okay, and critically, following the rules that I'm not explaining of how this EFT is constructed. Okay, the validity just requires when you introduce interactions, okay, which are going to be controlled by this parameter capital lambda, that capital lambda is bigger than h. Okay, so now I'm just going to turn a crank. Okay, I want to construct the soft de Sitter effective theory for the scalar fluctuations of the inflaton. We'll call them zeta, which is typical. Then I'm going to compute this coarse graining renormalization group equation for zeta. I'm going to do this integral transform to convert that equation into a Fokker-Planck equation. I'm going to solve for the probability distribution, and then I'm going to evaluate an observable which tells me whether or not I'm in this eternally inflating phase. Namely, I can use this to compute the volume of the reheating surface, okay? If it's finite, that means the entire universe reheated. But if it's infinite, that means the universe had never stopped reheating, okay? So that's a natural diagnostic for this question, am I eternally inflating or not? Okay, so this is what the result looks like. Okay, it's some differential equation for the probability distribution. I'm just showing it to you it's very concrete. I have the leading order Gaussian part that's very well known, and then the new thing we computed, which is this non-Gaussian correction. Notice it depends on two parameters, CS, the speed of sound, and C3. Okay, this is just following the terminology from the literature. In the Gaussian case, I turn this off, and I just solve for the steady state solution, and I get this probability distribution, okay, which tells me that the Gaussian fluctuations of zeta go like the square root of t. Okay, so it's a random walk with some Poissonian distribution, okay, in time. But then when I solve for the non-Gaussian, what I see is I get this new contribution, and if the zeta scales like t, not square root of t, then both of these are equally important, okay, and the non-Gaussian part can play a significant role in the evolution, okay? So the question is this ever relevant, or am I always in this Gaussian-dominated regime? And that's what I want to spend my last few minutes talking about, okay? Oh, good, and that leads us to this plot, okay? So now I showed you the formula that we use to basically compute this region, okay? And I'm rushed for time, but just to say that this perturbative validity is an attempt to basically test the Taylor expansion for the EFT of inflation. It's subtle for reasons we could talk about later. Okay, so here we are. Is this blue region really eternally inflating? Are we potentially in an eternally inflating universe according to Planck, or is there something else going on? So in order to answer that, let's turn, and by the way, again, I want to emphasize, maybe I haven't convinced you, but I've certainly followed all of the rules of EFT and of power counting, and I've made sure that at every step, my Taylor expansions were under control. Okay, so it is surprising. It was surprising to us when we first found this result that eternally inflating region was so big and so close to the region where you turn off the interactions. Okay, so now to understand this, let me turn to a toy model for fluctuating fields. Okay, And in particular, I want to tell you about random walks and the connection to this idea of coarse graining, okay? So I'm going to basically take two random walk models, a Gaussian random walk, where basically the step size of the walker is determined by a Gaussian distribution, and I'm going to compare that to a fixed step walker, okay, which basically goes either one step in one direction or one step in the other. This is a one-dimensional model, okay, super simple. And these two models have the same mean, they have the same standard deviation, okay? So I could just plot them, and from far away, they look the same, okay? But if I zoom in, I can see a difference. The fixed step walker is very sharp, right, because it's always in integer units, whereas the Gaussian walker looks smoother, okay? So again, you could see how a coarse graining description of this, you can't tell the difference. Some kind of EFT-like description might emerge as compared to zooming in and looking at the microscopics, okay? So we can do calculations. Again, these models are extremely simple, so we can compute everything. So let's ask, how far does a walker move in n steps? Okay, so let's let the distance the walker moves be capital X, and then we can just compute the probability to get a distance capital X, okay? Sorry for rushing, but I'm running out of time. And basically what we get is that the Gaussian is Gaussian. The fixed step walker, it's a little exercise in combinatorics, but it's doable. You can write down this closed form expression. And then if you take Stirling's approximation, you find the leading order thing is Gaussian, and there's some sub-leading corrections, okay? We see Gaussians as we expected because we all know about the central limit theorem, okay? So indeed, the central limit theorem emerges as some kind of universal description of random walks. And we can organize the information which characterizes the probability distribution, which is namely expectation values, okay? It turns out to be convenient to take this expectation value. We can organize this as some kind of expansion in so-called connected correlators, okay? As basically you have to subtract off a little bit to get this to be just right. Nonetheless, we can plug this in and we get something that looks universal. And then if the integral support is dominated by basically modes of order square root of n, then, which is Gaussian approximation, then we find that you only need to know the mean and the standard deviation to properly characterize the random walker to very good approximation, okay? And indeed, there's even a very real sense of coarse graining, which is basically if I do this rescaling, I can make completely manifest that all I get is Gaussian plus corrections that are suppressed in the large n limit, okay? So there's a very real sense in which the central limit theorem is coarse graining. It's UV insensitive, okay? And for those of you who know the terminology, we can think of the mean as being a relevant parameter, the standard deviation being marginal. These are all we need to know to determine the IR, namely the central limit theorem, compared to irrelevant operators which encode the UV sensitivity, okay? So now let me ask a different question, seemingly innocuous. Let's consider the probability of finding the walker where the distance is n. Remember, the steps are 1 unit or standard deviation 1 unit, okay? So what's the probability that the walker went further than n in n steps, okay? Well, already, when we ask this question, we can see that we expect there to be some dependence on the model. Because the fixed step walker, the answer is just 0. There is no possible walk you can construct that's non-zero, because the most it could do is it could go all in the same direction in n steps, which would give you x equals n. So the probability is just strictly 0 for x greater than n. For the Gaussian walker, of course, we have some wiggle room there, and so the Gaussian walker must have some non-zero probability to get this far, okay? And that's encoded in what's called the large deviation principle, okay? And so basically the idea is, if we ask for these exponentially sensitive operators, okay, as Dick foreshadowed, then what we're going to find is the naive expectation from the central limit theorem, which is that this goes like e to the theta times something square root of n, actually fails because, in fact, when you just do the calculation, you find that you get e to the n, something that's exponentially larger, okay? So this question about the walker, probability for the walker to go further than n in n steps is not captured by the central limit theorem, okay? And in fact, pictorially, what we're finding, what this tells us is the central limit theorem would say this is the way to get to n and n steps, okay? But this is suppressed by e to the minus n squared because there's this huge jump, okay? What actually happens is the large deviation principle is dominated by solutions that look like this, where most of your steps went in the same direction, okay? All right, so unfortunately, due to time, I'm gonna rush through this, but basically the point is that you can characterize distributions that satisfy this kind of scaling, e to the minus n times some order 1 function, and what the large deviation principle does is it gives us the tools to actually compute this so-called rate function, okay? So here's our two examples. This is the rate function for the Gaussian. This is the rate function for the fixed step walker. And this is what they look like, okay? So when we're of order root n, right, towards the center of the distribution, everybody looks the same, it's just Gaussian. But then when we go out into the tails, right, the rate function for the fixed step walker ends at 1. Okay, this is all rescaled by n, whereas the Gaussian continues out, and you can see the difference in the probability distribution, okay? So the central idea, no pun intended, of the large deviation principle is this Cramer's theorem, which is an elementary proof, at least at the level of rigor for physicists. And the key step here, I'm not going to go through the details, but the key step is that at some point, in order to evaluate this integral, I need to approximate it as a saddle point, okay? So here come together all of these ideas, is that the large deviation principle, okay, which is governing fluctuations in the tails of our distributions, is dominated by a different saddle than the central limit theorem, okay? So when we go back to this question of applying this to inflation, we have this notion that the Gaussian theory gives us typical fluctuations where this zeta goes like square root of t, okay? If I replace t by n, this looks exactly like the central limit theorem. Whereas the phase transition to eternal inflation is dominated by zeta of order t. And here we see that, in fact, the central limit theorem should fail, and we should be dominated by a new saddle, namely that it should be governed by this large deviation principle, okay? So the resolution to this surprising claim that this huge region of parameter space where the couplings are small would lead to eternal inflation is boiling down to the fact that we were secretly invoking the central limit theorem while asking a question that's maximally sensitive to the tail of the distribution, okay? But for those of you who are familiar with these ideas of effective field theory, it's very much counter to the reason that effective theory would break down, because there's no large energy associated with this. There's no obvious problem with the approach. Nonetheless, because of the kinds of questions that we were asking, we found that we were actually probing the tail of the distribution in an exponential way, where this new saddle kicks in. Okay, and in conversation, I can tell you a lot more detail about what that looks like. But the point is that this intuition that the phase transition to eternal inflation is probing rare events, it's probing the tail, is now realized in this concrete connection to the large deviation principle, which tells us that if we want to ask this question, we need to go beyond the standard effective field theory approach, and we need to look for new saddle points of the path integral, okay? And so just to quickly recap, what did I do? I told you a little bit about effective field theory, and then I told you how to apply those ideas to compute corrections to this paradigm of stochastic inflation. Then we applied this to inflation, okay? And we asked this question about whether or not our universe is eternally inflating. In order to diagnose this question, we turned to these simple toy models of random walks, where we saw a connection between coarse graining and the central limit theorem, and we saw this surprising failure of the central limit theorem through the lens of the large deviation principle. And that gives us the insight that the transition to eternal inflation is UV sensitive. So unfortunately, where I'm leaving you today is that this is still an open question, okay? Nobody knows how to evaluate the correct analog of this blue region. It's something we're actively thinking about, but I am quite convinced that the ideas and technology from the large deviation principle will play a role, and that the key is going to be to find the right example model where we can actually do these calculations, where we can find this saddle point. And like I was saying to Mike earlier, there are examples in more standard quantum field theory where this can be done. So I'm really quite confident that we can figure it out, given enough time, okay? So the take home here is, I want to leave you with this idea that fluctuations of field in de Sitter space can be connected to some kind of renormalization group evolution in an effective theory. That typical fluctuations are governed by the central limit theorem, which leads to a notion of model independence. Okay, the coarse graining gives us a couple of parameters, basically the mean and the standard deviation, which govern the typical fluctuations. But that rare fluctuations, namely those that are exponentially sensitive to the tails, are governed by the so-called large deviation principle, which brings back in sensitivity to the detailed microscopic description. Okay, so what do we want to do in the future? Well, I already said, one of the main goals is to just find a reliable calculation of this phase transition to eternal inflation in a theory with interactions, okay? To my knowledge, this hasn't been done. Nobody knows how to do this. So just finding an example and showing that you can do it robustly, I think is going to be extremely interesting and will lead to a lot of insight. We're also looking for new applications of the large deviation principle. Now that we stumbled onto this, it's a rich mathematical literature. There are all kinds of connections to statistical mechanics. People have applied this in some astrophysical systems in a couple of places. We actually cite in our paper, I found about 10 references that connect the large deviation principle to physics. But I think there's a lot more to be mined there. It's really an amazing idea that I think is going to lead to all kinds of interesting applications. And then there's all kinds of stuff to do with this soft de Sitter effective theory. It's brand new. There are so many open questions, things we're exploring now that I'm happy to tell you about later. And finally, I want to say this also has motivated us to think a lot about just novel random walks, quantum walks, the surprising richness of just studying random walk models. Well, it was surprising to me. I think people who do, say, polymer physics are very familiar with this, but I think there's all kinds of, again, gold to be mined just thinking about random walks. Okay, thank you very much. Sorry for going over.
You gave a lead slide that appeared a couple of times on different energy scales.
Yeah.
Can you go over some of the quantities in that look somewhat familiar, but I'm not sure I understand.
You mean
Yes.
this one?
Yes, okay, what is F pi here? I think I've seen in other contexts.
Yeah, good. So so I didn't explain this at all.
Yeah.
Let me go back to even the simpler one first, and then we'll come back to this one. So so this is like the general picture for EFT. Okay. So so the idea is that we have some fundamental UV theory, and at a scale associated, say the simplest case is a theory with a heavy particle and a light particle. So big M is the mass of the heavy particle. And what we want to do is we want to write down an effective field theory, which is only characterized in terms of a light particle, right? So that's what we're doing when we cross this line, okay? And then at low energies, we just see the light particle and we can make predictions, okay? So now, let me say there's a very important example where we try to do this and fail in particle physics, which is quantum chromodynamics, right? So in QCD, we know the theory is quarks and gluons, and we have this effective description of pions called the Chiral-Lagrangian, but we actually don't know systematically how to cross this line, okay? So that's exactly the same style of EFT that's the EFT of inflation. So when we write this this kind of diagram, okay, we're not writing down the microscopic description actually. We're only characterizing the low energy theory, and the low energy theory is characterized by basically two parameters, okay? One is what we're going to call F pi, just because it's a very close analogy with pions, okay? So this is the so-called pion decay constant, right?
But why is that related to phi dot? That's what's confusing me.
Yeah, well, because F pi is the scale of spontaneous symmetry breaking, and the EFT of inflation is the theory, which is the theory of spontaneously broken time translation invariance. Okay? So the real way this is constructed is what these guys realized is that there should be an EFT that emerges due to the fact that the background breaks time translation invariance. Okay? And that breaking of time translation invariance should give us a Goldstone boson. And that Goldstone boson is characterized by a Goldstone boson decay of constant F pi. F pi is the scale of symmetry breaking, and what's breaking the symmetry is phi dot. So that's why F pi is, so from the particle physics point of view, they think of it as F pi as the symmetry breaking scale, okay? But from cosmology, right, the symmetry breaking is coming from the time evolution of the
But
field.
then what is the Goldstone boson in this context?
Yeah, so the Goldstone boson is the scalar fluctuations of the inflaton inside. And so, so this gives you, at leading order, it basically drops out, right? But in subleading order, it becomes very important for understanding the scales that appear. And so then what's drawn here in sort of two different contexts is the scale where we add additional interactions, okay? So that comes with some other parameter, lambda, and in fact, in detail, lambda is actually set by the speed of sound times F pi. Okay, so again, in the sort of EFT parlance, we would call this lambda, but a cosmologist would say, oh, there's some scale associated with the theory breaking down with the interactions, which is CS times F pi, okay? And sort of equivalently, it could be the scale of,
Which could be either larger than or greater than that.
exactly. And so then you need to understand, you know, when you do these calculations, you need to understand what the expansion is. And if you just work order by order in perturbation theory, what you find is that the expansion is in H over lambda, okay? So H, if you like here, forget H dot, H is like the IR scale, right? So this is in my picture for quantum chromodynamics, F pi would be like the line between the fundamental theory and the EFT, and H would be like the mass of the pions, okay? So the rate, and indeed, an exact analogy with QCD, when you do loop calculations, you would find corrections that go like m pi divided by some scale associated with interactions. And indeed, that's exactly what you find in the EFT of inflation. You get H over lambda when you do correlators, okay? What's shocking, and because I didn't pace myself so well, I ran out of time, is that this calculation, so then actually I can show you here, okay? The thing that was surprising and really the hint that something new was going on here is that when we calculate this inequality which determines the phase transition to eternal inflation, what we're finding is not H over lambda, but F pi over lambda. And that's a genuinely new effect, okay? And so, and indeed, because the speed of sound can vary depending on the parameters of the model, right? You can have lambda be above or below F pi. And so but this scaling you would never see if you just did perturbative calculations, okay? So that was the real surprise, and then the puzzle which led us down this rabbit hole of investigating the large deviation principle.
Okay, I'm gonna suggest that we give Tim a chance to catch his breath. There will be refreshments upstairs, and Tim is around for the next day. So let's thank you, Tim, again for
Sure, I can still.